All right. So what I'll do is I'll go through this practice test, and each one's on a different kind of problem. Um, and okay, and so I'll talk about that general type of problem here. But I will let you guys. Well, okay. As far as the practice test goes, on Monday I talked about problem 6, and I also talked about problem 3. So of remaining problems, 1, 2, 4, 5, which would you like me to talk about the most?
5.
Yes. 5. Okay. All right. Now, so problem 5 on the real test is going to be either cylindrical or spherical. I mean, I only have room for 6 problems, so I had to pick one of these. And in this problem, on the practice test, happens to be cylindrical. So you can guess what I'm going to do from there. But anything that can be said about these changes of variables can be helpful. Okay, so we're integrating 4 over this solid. So really we're computing with volume. Oh, there's some napkin fragments there. So it's going to be 4 times the volume of the solid. So E is bounded by z equals 25, and the paraboloid z is equal to x squared plus y squared. Now, with all of these, especially with triple integrals, it's helpful to have some visualizations of what's going on. No, you don't have to know how to draw a really decent paraboloid, but just a general idea that when you have this plane, z equals 25 up here, and then a paraboloid coming up to it. And we've seen the paraboloid a lot. So it's something that hopefully you're used to by now. And because we have x squared plus y squared in here, that suggests using cylindrical coordinates. Whereas if you see in the description of your domain or your integrand, x squared plus y squared plus z squared, that would suggest spherical coordinates, where this would just be rho squared. Here you have x squared plus y squared in polar or cylindrical would just be r squared. So those are your tip-offs as to whether you should make a change of variable at all, and if so, which one. Okay. Now, so what we can see from this solid, this bounded by this plane and this paraboloid, is you need to understand the intersection of these two. And what you can see is that the intersection of these two is going to be a circle. And the radius of that circle is going to indicate what your limits will be in R. So what you can do is take your boundaries in Z and equate them. So what we have is x squared plus y squared, which happens to be r squared, is 25. So for the intersections of these two, that tells you what your limit should be in R. So this is cylindrical, so we need limits in R, theta, and Z. Okay. Now, from visualizing this, we have that the upper limit on Z is going to be 25. And the lower limit in Z is going to be the paraboloid. But that's going to be Z is equal to R squared. So that was what will give you, so whatever's the bottom gives you the lower limit, whatever's on top gives you the upper limit. So those are going to be your innermost limits. Now what about the limits on R and theta?
Would R be 0 to 5?
Yeah, because r squared equals 25 marks the intersection. So what we have here at the top is r is equal to 5. So r is varying. R only goes up to 0 down here, and then up to 5 up here. So yeah, 0 to 5. So that defines the extent of a domain. But what's happening is, for a given r and theta, say if you're looking at a point out here in terms of r and theta, what's z? Z is going from down here, so right here is where z is equal to r squared, and going up to
25.
here, yeah, z equals 25. So that's how the integration is happening, is that r and theta are going to be your outer limits, because those limits can be made constant. Z's are not constant, so those should be on the inside. So what is, for any given r and theta, so in other words, any point within this circle on the top, what is the extent of z? It's going from here to here, so that's why it's lower limit to upper limit. What about theta?
0
to 2 pi.
Yeah, we're going all the way around, because there's no upper boundary specified. Like, for instance, if there had also been another boundary, like for placing limitations on x and y, then that would have the effect of limiting the range of theta. But we don't have that here. So those are the limits of your integral. So your new integral is now going to be, so from 0 to 2 pi and theta, unless there's some compelling reason to do otherwise, you might as well always make theta the outermost limits for constant. Okay, 0 to 5 in r, and then r squared to 25 in z. There's your integrand, and we have dz, dr, d theta, and what else do we need? R, the extra factor, or Jacobian. Okay. Although since your inner integrals with respect to z, you could take, well actually, before you could pull out all the way. And the theta integral can be separated from everything else, because nothing else depends on theta. And what's left is 0 to 5, and then r squared. Okay, the r can go out here, and then you have r squared to 25 dz. Yeah, of 1 is your implied integrand. So you could work it out that way.
So I'm sort of confused on how you would work it in spherical coordinates. I mean, should z equals x squared plus y squared plus z squared, how would the setup go?
Well, first of all, it would be questionable whether it's even a good idea to do this in spherical. Because what could happen, if you choose a bad coordinate system, your limits would just be so complicated that maybe the integral couldn't even be done. Now, like, I could see where, because you could express z in terms of x squared plus, well, what you're doing in that case is you're equating z equals 25 to, okay, so in this case you have...
Well, what I'm really asking is can we do a problem in which we would use spherical coordinates just to alleviate any confusion that I might still have? Okay. Because you said there's a chance that you would put a problem with spherical.
Let's see. Okay, what I can do is, all right, because I pretty much remember what I put on the test a couple weeks ago for the real test problem, so I can give something that's distinct from that. Okay, so I will. Okay, I'm gonna try making up a problem involving spherical. Oh, well, first, any questions about the setup of this one, though?
Is that what it asks for? Is this to set it up?
No, for that one you have to work it out, but that's done in the solution, so you can look there. I figure most questions will be about setup. Okay. Big is a volume problem. Find a volume of a solid E bounded by the sphere x squared plus y squared plus z squared is equal to, say, 4. And the plane z is equal to, I'll say z is equal to 2. Okay. Again, I'm making this up on the fly. I don't know if this is going to be manageable, but it should show you something about setup. So what we have here is, so you have a sphere, so what's the radius of the sphere? Yeah, 2. You take a square root of that. So you know right off the bat that rho, which is your distance variable in spherical coordinates, cannot possibly go beyond 2. But then you have a plane that is cutting through. So you have some intersection of this plane of a sphere that's marking the bottom part of your domain. And I needed to pick, oh wait, not a good idea. Okay, let's change this to 9. No, I can change this to 1. Okay, so z equals 1. Yeah, as I said, I had to pick a z that's less than that, or you get, well then, actually it's probably really easy in that case. What do you get? If I put z equals 2. So, well, it'd be between z equals 2, but where these two intersect, they intersect at a point. So the volume would have been 0 in that case. Okay, so, all right, so we have this kind of situation, and we need limits on rho, theta, and phi. Okay. So what's happening in this case, as far as the origin is concerned, if we draw a side view of what's happening, so here we have our sphere that goes up to 2, and then we have this plane z equals 1 cutting through that. So we have to figure out what's the, how does this affect the limits? Now, we see that having this situation, we're still going to cover all the possible theta values. We're still going to go all the way around the sphere. So theta will go from 0 to 2 pi. Whereas if I had specified some other like vertical plane cutting through this, that would have affected my limits for theta. But we need to look at this picture to understand the relationship between rho and phi. Because phi is our angle that sweeps down from here. Like phi equals 0 is the North Pole, phi equals pi over 2 is the equator, and so forth. So we need to see what limits of phi we would want. Where these two intersect, because this is x squared plus y squared plus z squared is equal to 4. So if I set these two equal to each other, so at the intersection, that would be x squared plus y squared plus 1 squared, because z is 1 on this intersection, is equal to 4. So x squared plus y squared is equal to 3. So in other words, the intersection of the plane and the sphere is a circle. X squared plus y squared is equal to 3. I was starting to think that this problem might also have been easier if done in cylindrical, because this gives you a nice constraint on x squared plus y squared. But if we forge ahead with spherical, this is what I get for trying to make a problem up on the fly.
Would you like me to get one off of the homework?
What?
Would you like me to choose one off the homework?
Go ahead and pull one up if you can. But okay. So because what's happening is for any particular value of phi, like phi is going to go from here all the way down to here, where z is equal to 1. Okay. So, and this distance right here is going to be the same as this. Like here we have a radius of square root of 3. So we have this right triangle, and rho, of course, is equal to 2. This distance, because we're going all the way out to the boundary of the sphere. So what that tells us is phi is going to start from 0, the North Pole, and go all the way down to here, to what this angle is. And how do we get that? The angle, phi, where this meets, satisfies tangent of phi is equal to opposite over adjacent, 1 over the square root of 3. And that happens to be satisfied, phi is equal to pi over 6. So just working out what angle this is where these meet gives us that limit. So, okay. So it really comes from that picture, we need that. And then for any particular phi, you have to figure out what is the rho value from here to here. Your upper limit on rho, certainly, is going to be 2. The lower limit is where these two meet. And the thing is, here's where you use the fact that z is equal to rho cosine of phi. And right here, z is equal to 1. So for the lower limits, 1 is equal to rho cosine phi. So that means rho is equal to 1 over cosine, so secant of phi. So secant of phi is the lower limit. So those would be the limits of integration, and that means that at least you have constant limits for theta and phi. Rho would have to be your innermost integral, because that has a non-constant limit. Now the point of all this, which one common theme of both problems, is limits were figured out by seeing where things intersect, where your boundaries intersect. So the intersection of this boundary leads me to this equation, x squared plus y squared is equal to 3, and it was that intersection, at this point and also here, that leads me to the lower limits for lower and actually is upper limit for phi and a lower limit for rho. Any questions about this? Yes.
When you found pi over 6, did you was there any math behind finding pi over 6?
Knowing your basic angles.
Okay. Just eyeballed it.
Yeah, because so sine over cosine, and if you how you get your basic values, you have so it's 1 over square root of 3, but that's the same as 1/2 over square root of 3 over 2. So sine has to be 1/2 and cosine has to be that. And that's where the 30 degrees or pi over 6 comes from. Or you can use your calculator.
Still trying to find is this 14.4?
14 points, I believe it's 14.5.
So, what are the odds of us having a cylindrical versus spherical?
Absolutely. the thing is, I was trying to come up with an example that was not trivial, which, of course, made the effect of having it. Of course, when you do that, then you run the risk of having something that's too hard. A more typical example would be, for instance, using the, like, say, a whole half sphere. Like, if it was the entire, so if the boundary was not z equals 1, but z equals 0, then that would be a whole lot easier, because then you would just say rho is going from 0 to 2, and then phi would be going from, you know what, I'm so sorry, I goofed here. This angle is pi over 6. Phi is the angle sweeping down here. So this is actually 90 degrees minus phi. So this angle will be 0 to pi over 3. So I just had the opposite angle. I apologize. Remember, North Pole, South Pole, equator. So I got caught up in this whole standard position crap. So phi equals 0 is up here, pi over 2 is down here, pi is down below. Okay. All right. Okay, it's instead of time, I need to erase this. Remind me to never make a promise on the fly again. Yeah. The thing is, when you have boundaries like that, like x equals something, or z equals something, mixed with polar or spherical coordinates, that's when you get these crazy equations. Okay. All right, so this is one of the homework problems. Find the volume of a region that is outside the cone, described by phi is equal to pi over 4. So that's nice to give you one of the limits in the problem. And then inside the sphere, rho is equal to 6 cosine phi. Okay. Now, in fact, this is kind of like, okay, you can set it down if you want, but, okay. Now, it's kind of like one of the other problems on the practice test, where before you had, I gave you a problem that had, like r equals 4 sine theta, and you end up getting a circle sitting on top of the x-axis. This is kind of similar. If so, what happens is, if phi is equal to 0, so you're at the North Pole, you get rho is equal to 6, so you're all the way up here. But then, as phi sweeps around, like down towards pi over 2, like when phi is equal to pi over 2, that means that rho is 0. So you end up having this kind of situation. So it's a sphere that is sitting on top of the xy plane, or z equals 0. So it's actually a sphere of radius 3. So when you get an equation like this, like there's this in polar coordinates or this in spherical coordinates, it's good to see what happens for certain key values of phi. Like when phi equals 0, phi equals like pi over 4 or pi over 2, the ones that are easy to get, and see what kind of shape you're really dealing with. Because looking at this equation, if a problem said it's a sphere, and if not, you wouldn't really know that this was a sphere until you actually tried to graph it. And now, anytime you have a constant phi value like this, pi over 4, yeah, that's a cone. So you have a situation like this. Okay, so phi is equal to pi over 4. Now, we need limits. So limits on rho, theta, and phi. Okay. Now, these are the only boundaries. There's nothing to restrict theta from making its journey from 0 to 2 pi. So theta is set. Now, obviously, okay, it's this region that's So it's, oh, this is kind of strange. Because they want it outside the cone and inside the sphere. Actually, see what they have in the picture, because I want to make sure that the problem is being interpreted correctly. Sorry, I hope you still had it up.
You're gonna have to.
Oh, it's your computer. Okay.
Yeah. Okay.
Oh, something go wrong?
I think he exited.
Yeah, I exited. I know the answer, but
That's not the answer I wanted. So, okay, because I'm assuming what they mean that it's out that they're talking about this region right here, because that would be outside the cone certainly, but it's still within the sphere.
That one doesn't work.
What?
what doesn't work?
It's not a person set me on that one.
Okay.
We have to do this one. Non-mixed different and then get rid of that to work.
Okay. So we'll have to go with this assumption. Okay. Now, the thing is, let's talk about the phi limits, but please keep trying to pull that up if you can. So pi over 4 is obviously a limit, but is it the lower limit or the upper limit? And what would the upper limit be? No.
We're talking about phi, right?
Okay.
It's not exactly
Oh,
the
so
same
it's not rho,
numbers,
phi.
but the graph looks like this. There's the area of the sphere that's sticking out of the cone.
Yeah. It says outside the cone and inside the sphere. Unfortunately, the pictures.
Here it is.
Okay. Yeah, I see the picture. So, yeah. I'm going to go with, based on the verbiage, that it's this. But because obviously, whether you're doing this or this, when I say outside the cone, it makes me think it's out here. So that's where I'm going with that. But we don't have time to work out. Again, we're going to focus on the setup anyway. No, so pi over 4 is actually, in this, based on what I've shaded, is actually going to be the lower limit. What's the upper limit?
Why would it be the lower limit?
Because where does phi equals 0 start? At the North Pole. So phi equals 0. Small values of phi are up here. That's outside the shaded region.
So your upper limit would be pi over 2.
Yeah. So over here, so halfway between the North Pole and equator, down to the equator. So yeah, pi over 2. Okay. Now, so keep in mind phi, and again, I apologize for my mistake earlier, so please remember, it starts here, sweeps down that way. That's the opposite of what you're used to, because with polar coordinates and all the trig you've ever had, you're accustomed to, theta starting from 0 down here and sweeping that way. Phi works the opposite. You have to remember that. Okay. Okay, so really burn that into your brain. Okay, now, the last thing is rho. Now, to get an idea of how rho is behaving, it's distance from the origin. So you have to start from the origin, and you work your way out. Now, for any particular value of phi, you're starting at the origin, and you're going from here to here. So, based on the problem description, what should the limits on rho be?
0.
Yeah, 0 is the lower limit because the origin is included for any particular value of phi. And the information is there on the board as to what the other limit should be.
Would it be 6 minus pi over 4?
No? What did you have?
6 cosine phi.
Yeah, the sphere. The sphere
Okay.
marks the boundary. So keep in mind, of the shapes you're given, we have a cone, we have a sphere, which one is marking the boundary? Use its equation to figure out, to get the limit. So those are your limits. So rho has to be inside because it has a limit that depends on phi. So your volume is going to be integral from, 0 to 2 pi in theta, pi over 4 to pi over 2 in phi, and then 0 to 6 cosine phi in rho. And what is the extra factor? For spherical, it's different.
Rho squared.
Sine.
Sine
Phi.
Sine.
phi. Yes. Okay. So that's what your extra factor, and then you have d rho, d phi, d theta. And at least the integral itself won't be difficult from there. You can, well, see. Yes, so when you integrate this with respect to rho, you're going to get rho cubed over 3, and then you would plug in that. So you're going to wind up with cosine. Okay, so, well, we're going to get 2 pi because of the theta integral.
So our extra factor is the only thing in our interval?
Yeah, because it's a volume problem. Your integrand is 1 if it's volume. Yeah, if they've given something else, integrate whatever function, then that would be in here too. So remember, volume is you're starting with 1. And then you'd have sine phi, and then this would give rho cubed over 3, but that's going to be 216 cosine cubed phi over 3 d phi. So that is after working out because 216 is 6 cubed. So after working out the intervals integral with respect to rho, this is what you get. And to work out the rest of it, you use a substitution. U is equal to cosine phi. Therefore, du is minus sine phi d phi, and you have a sine sitting right there. And then you can work out the rest of the integral from there. Okay, we have used way too much time on spherical coordinates. Does anyone please have any questions about anything else? Problems 1, 2, or 4? What?
I think I remember getting problem 4 wrong when I was working it.
Okay, so here we have a triple. Okay, sorry for anyone watching at home. Oh, attendance. Oh, I put in all the attendance information I have into MyLabs Plus. Not too many people have 100. And some have a lot less than that. Remember, it counts 10% of your grade, so you pull this not showing up stuff, that really is going to hurt you. If someone doesn't show up at all, yes. I don't think anybody's in that boat, but okay. But yeah, certainly matters in borderline case. So number 4, we have okay, 0 to 1. So the whole integral this time is set up as it's given. And then we have okay, x e to the y sine z dz dy dx. Now, since all the limits are constant, this can be pulled apart into a product of 3 single integrals. So for dx, we have 0 to 1 x dx. Then for y, we have 0 to 2 e to the y dy. And then we have minus 1 to 1 sine z dz. Now, the shortcut for this is this integral is equal to 0 because the integral over symmetric intervals, so the limits are negatives of each other, equals 0 if f is an odd function. So that's the quick way to do this one. Where an odd function is where you negate x and negates the function. So that means odd powers of x, also sine, also tangent. Those are examples of odd functions. Even powers of x, or cosine, would qualify as an even function, but this only works for an odd function. And that's a good thing to keep in mind because I wouldn't be surprised if you you go ahead and integrate this regularly. But especially with odd functions and limits like this where we're negatives of each other, good chance of a sign mistake. And I don't know if that's what happened in your case, but that's why these things are good time savers. But if this had been, for instance, okay, to make it more interesting, say if this had been cosine z. So here, cosine is an even function. It's not 0, but you can write it as 2 integral from 0 to 1. So you can cut the interval in half and then just double the integral. And in fact, if that happens, you recognize you have an even function, I would recommend this because it'd be easier to work with 0 as a limit than having negatives, because again, you're begging to make a sign mistake. So then you would have 2 sine z from 0 to 1, so you just have 2 cosine of 1, which is not any value in particular, you need a calculator for that. And then you can just work out these integrals from 0 to 2, and then x squared over 2 from 0 to 1. So you'd have, so the value of this integral altogether would be 1/2 from that, e to the y minus 1. This is why you'd be careful with exponentials, especially, because a lot of times, your lower limit is 0, and you think, oh, don't need to plug that in, you're not going to get anything. But yeah, you do, when it's exponential or also cosine.
And not e squared.
Yes, actually plugging in the upper limit, yes. E squared minus 1 times whatever this integral is, which was 0 in this case. But if I had made it cosine instead of sine, it would have been this instead.
So our whole thing's 0.
Yeah, in this practice test problem, yes, it's 0.
So if we just worked out the first integral, that's sine z dz,
Yeah.
and we found it was 0, we can automatically assume the entire thing is 0. Are you
Yes.
going to require us to work out the other integrals?
No, I mean, once you get an answer, you're done.
Okay.
Yeah, because I mean, this is something that I want to encourage you guys to keep in mind and use if it comes up.
And negative. It's negative.
What? Okay, yeah. Okay. Any other questions? This is the last chance.
I was going to ask about number 3. I know we go over it. I think we went over it, didn't we?
We talked about it last time, a little bit.
I was just sort of confused on how x equaled the 4 sine theta.
Oh,
That one part.
the 4 sine theta is for the limit. X is replaced by r cosine theta in the integrand. So, yeah, for number 3, you have integral of x dA. And given the once,
Okay, I see.
Yeah.
I see.
and then yeah, x is r cosine theta, extra factor of r. So everyone else can see. That's what was asked about. Okay. So, but yeah, the thing to remember, if it's not clear from the description of the problem, what the limits will be, because sometimes they might be given to you, or it's just pretty much given to you in the description of a domain. But if it's not, use intersections. So every more challenging problem we did today, limits came about by figuring out an intersection. And for cylindrical coordinates, it's a good idea to draw what's happening like in the xy plane. Focus on x and y to figure out what your limits in r and theta. For spherical coordinates, do what I did actually in both of these examples. If you draw what's happening in, so this is like the xy plane, and this is z, and you can see what's happening for your limits. So phi is going this way from 0 to pi over 2 and then continuing on to pi. So to figure out your phi limits, keep in mind that phi is sweeping this way. To figure out your rho limits, keep in mind that rho is starting at the origin and emanating out this way. So use the meanings, you need to use the meanings of these variables to figure out what your limits are. And then similarly for polar and cylindrical, there you're working in the xy plane, and bad circle, I know. So r, in this case, is distance from the point x and y equals 0 to figure out your limits in r, and then theta, of course, is sweeping this way as angles usually do. So, so the meaning of each of these variables, rho, theta, r and theta, or rho, theta, and phi, are needed to figure out what is your lower limit, what is your upper limit. I would suggest, I'll tell you what I'll do, since I'll have, well, when I do have time. I'll take the example that I made up and write that up and post it. So, because trying to do it on the fly, it's not as clear as it needs to be. But you see, that's like the worst case of how do you get limits. But I try not to make the problems on the test all that onerous as far as figuring out what the limit should be. But I think it's a pretty good example to illustrate why I need to know how these variables work to get the limits. Okay, so I'll stick around for any last questions anyone has, but see you Friday.